All right, here we go, everybody. 11.2 notes and a video this time, I promised. Okay, so just a reminder as we get started, remember that you have Math Excel due tonight on Tuesday if you're watching this on Tuesday, or last night if you're watching this on Wednesday. So there was Math Excel due on the 24th, so make sure you do that. You have a Power School daily quiz that you need to do anytime over the 2 days, Tuesday, Wednesday. And then we're going to do notes. And at the bottom of the notes, there's a Desmos activity that I want you to complete so that you can get points for today. And then Math Excel due on Thursday too. So make sure that you get all of those things done. It's all listed in the agenda. All right, today we're going to talk specifically about probability, and some of this information you may have heard before. So if you have, that's great, and this will just be a little review. Some of the other things like experimental probability might be a little different for you. So let's get started. When we talk about probability, we're talking about how likely things are to happen. And when they might happen, we have a range from 0, they never happened, to 1, they happened every single time. So when we talk about probability, our values are always going to be written from 0 to 1. But we can write those probabilities in a bunch of different forms. So we can write them as integers, 0 and 1, and their corresponding parts would be fractions. So 1/2, 1/4, 1/5, 2/9, etc. Or we can change all of those fractions to decimals. So again, 0 or 1.0, and then 0.5 and 0.2 and 0.3. Or we can write them as percents. So 0%, 100% would be 1, and then 50% would be that equally likely in the middle. So any of our probabilities can show up between 0 and 1, and they would be written as a fraction or a decimal or percentage. So when we talk about probability for the entire length of this lesson, those are the numbers we're looking for. Probability comes in two types. It comes in experimental and theoretical. Let's start with experimental. So experimental probability is when you're talking about the number of times an event actually happened that you tested out of the total number of times that you tested it. Whenever we're doing experimental probability problems, especially in our math textbook or in practice or whatever, they usually have to give you both of those numbers, the number of times that event actually occurred and the total number of times they tested something. So when you're looking at your probability numbers or probability problems and you see both numbers, the number of times it happened and the number of times it tested, that's probably an experimental probability problem. If we're talking about flipping a coin for experimental probability, we would actually go through and we would flip our coin, let's say 10 times, and we would record how many times we got heads out of those 10 times. Now, you all know that if you flip a coin, it is not always going to land one time on heads, one time on tails, one time on heads, one time on tails. So when I flip my coin 10 times, we can get a number somewhere between anywhere from 0 times we got heads to 10 times we got heads. Sometimes those are likely, sometimes those are not as likely. So when we talk about experimental probability, we are recording the actual number of times something happened during our quote unquote experiment, or the number of times we tested something. That is different than theoretical probability, which is the kind you probably have heard about before. And that's talking about the number of times you think something could happen out of your total number of times. So this kind is, again, when you're flipping a coin, we think because there's one side that says heads and one side that says tails, then there should always be a 50-50 shot or a 1/2 shot that you're going to get heads out of tails, or heads instead of tails each time you flip the coin. So in theoretical flipping of coins, heads shows up 50%. But if I actually flipped my coin 10 times, experimental probability would tell us actually how many times the heads showed up. So those are the two differences between those. Again, in your problems, experimental probability, they have to tell you both of those numbers. So look for two numbers, something out of something. With theoretical probability, you have to think about how many times those things might happen, and they would be on things like dice or cards or flipping a coin, things you have seen before you could picture, spinners, etc. Okay. All right. A couple of more key terms here before we continue. A simulation is when you model an event, and we're going to do a simulation in one of our practice problems. Sample space is the set of all possible outcomes. So when you think about how many total times that could happen, that's your sample space. And if your outcome in your sample space has the same chance of occurring, then those outcomes are considered to be equally likely outcomes. So again, in that theoretical probability of heads versus tails, I said that we really should be 50-50. So heads and tails should have equally likely outcomes. That is not always the case, but if you do it a lot of times where you flip that coin, then you end up with about 50-50 times. Okay. Before we do our practice problems, I want to go over one more thing on your calculator. Let me get that all on one screen there. So during one of our sample problems, it's going to ask us to create a simulation, and you can create a simulation on your calculator. So if you go through and you press the math button on your calculator, use your arrow key to go over to the probability menu. Some of you already did this when you did permutations and combinations, if you didn't have the shortcut. But option number 5 says rand int. That stands for random integer. So if you choose option number 5, you can type in the two numbers that you want your random numbers to appear between, and then how many times you want that random number to come out. So if I type in rand int 528, then that's going to pick 8 numbers between 5 and 20. And when you hit enter, it will give you 8 numbers between 5 and 20. You can do that again and again, and we'll do it on our problem a lot of times. So you can do that multiple times on your calculator just by hitting enter after you've typed that in each time. So again, that's math, the arrow key over to the probability menu. You can see that screenshot with the probability menu at the bottom there with the random integer, and then what it looks like when you type it in on your calculator. Some of yours might look a little different, and you'll see that when we do our sample or our example with my calculator, but that is what it should end up looking like at the end. Okay. All right, let's get to some examples. So first example. Of the 60 vehicles in the parking lot, there are 15 pickup trucks. What's the experimental probability that it's a pickup truck? Number 1, they gave us 2 values. Number 2, they told us it was experimental. So since both values are given, that is experimental. We do 15 trucks out of 60 total vehicles. Plug that into your calculator and get your decimal out, and you get 0.25 or 25%. So that one's a pretty straightforward, especially because it told you experimental. Similarly, problem number 2 gave you 2 values, 20 out of 50, and then it also said the word experimental again in this problem. So 20 out of 50, put it in my calculator, 0.4, and that gave me 40%. So hopefully those first 2 experimental probabilities are pretty easy. And most experimental probabilities should be pretty easy. The hardest thing there might be if you have to count how many times that actually happened. We're actually going to do one of those counting in our simulation here. But they might give you a table of data and you have to count. But if it's just a straight up word problem, they're probably going to give you the 2 numbers. You write your ratio and go through and type that in on a calculator. Okay. So let's talk about this testing question. So I didn't finish this testing question yet because I wanted to show you it on the calculator. When you go through, it says on a multiple choice test, you have 4 choices. Normally we would think A, B, C, D, but we can't put A, B, C, D in our calculator. So we chose 1, 2, 3, 4, and only one of those choices is correct. You can pick whichever one you want. For the purposes of this problem, I'm going to choose 1 as the correct answer, and then 2, 3, 4 are the wrong answers. So how can you simulate guessing the answers? Well, we're going to use that random integer value on our calculator. So if you go to your calculator, remember, click the math button, go over to probability, and choose option number 5, random integer. We're going to say we want a number between 1 and 4, and we want 10 numbers to appear because there are 10 questions. Remember, if yours doesn't look quite like this, you still want to type the numbers 1, 4, 10 after random integer. And you'll see that's what shows up when I click this paste button. So if it looks like this on your calculator, then you're good to go. So we're choosing numbers between 1 and 4, 1, 2, 3, 4, integer numbers, and we're going to choose 10 numbers between 1, 2, 3, 4. So if I hit enter, it's going to spit me out 10 times where it chose the numbers between 1, 2, 3, 4. Remember, I told you that 1 is the correct answer and all the other numbers are wrong. So in a 10-question quiz, this means I got question number 2, question number 3, question number 5, and question number 10 correct because I got a 1 on all of those. So everywhere there's a 1, that's a correct answer. So 1, 2, 3, 4 correct answers. Everybody see that? All right, I'm going to hit the enter button again and run this again and keep running it until I run out of spaces. So hopefully that's 5 if I could fit that. I hope that doesn't go through and bump that up a little. Oh, it did just too much. I'm going to go back up so that I can copy this page so that we can have that. There we go. So I'm going to copy that screenshot into my notes here. Got to resize that. It's a little big. So there's our first 5 times that we took our test. Oops, what happened? Undo. There we go. Our first 5 times that we took our test and it went through and gave us how many correct answers. So then I'm going to do that again 5 more times. This time I got to count. So here's 1, 2, 3, 4, 5, and go back up a little. There we go. Copy that screen again. Chill out. So there's 5 times I went through and did this. And let's do it 5 more times just for good measure so we have a good set of sample spaces. So I'm going back to my calculator. And I'm going to hit 1, 2, 3, 4, 5. Go back up and get all of those options. All right. So basically, we ran this experiment 15 times where we tried to get 10, try to see how many right answers we got out of 10. And we want any time that it is 6 correct answers. So if you take a look through each of these, we can go through and highlight all of our correct answers. So oops, that did not work. Sorry about that. Here, here, here. Ooh, that one was terrible, huh? Those were all terrible. Remember, 1 is a correct answer. I thought we were looking good on that one. So if you take a look at all of those 15 times we practiced that, not in any of them did we ever get 6 answers correct. I don't think. Nope. I think the most we have is 4 answers correct in one test. So the experimental probability of getting a 6 out of 10 is actually 0 out of 15 or 0%. Now, if you really kept running this test, you probably would get at least 1, maybe 2 trials, but you can see that it's going to be a really low chance of getting 6 out of 10 answers correct. Okay, so you can simulate this on your calculator using that random integer feature. We want to find out what's the experimental probability of getting a 6 out of 10, and that's by we got none out of 15 problems. Okay. All right, and we had to count to get all of those. Let's finish up by talking about theoretical probability. So remember, theoretical probability is when you go through and you actually think about how many times something should happen. So the first one's pretty basic. If I wanted to get a 5 on a standard number cube, that's what we usually think of as a dice. It's anything with a 1 to 6 numbers on it. And then how many times would a 5 appear on that standard number cube? Well, the 5 only appears once. So 1 5 out of 6 numbers gives me a 1/6 theoretical probability of getting a 5. You probably have seen something like that before. Now, the next one's a little more difficult. This time we want a sum of 5 and we have to roll 2 dice. Now, remember, the dice have 1 to 6 on them, both cubes. So you can't get lower than a 1 on any dice, and you can't get higher than a 6. So when we think about that, that gives us a total of 36 possible numbers that we could get, 36 possible sums, because there's 6 for each cube. So 6 times 6 is 36. And we want to think about how could you make a 5? Well, we could make a 5 out of 1 and 4 and 2 and 3. 1 and 4 can happen with a 1 on the first dice and a 4 on the second, or it could be a 4 on the first and then a 1 on the second. So that happens twice, 1 plus 4. 2 plus 3 also happens twice, 2 and then 3, or 3 and then 2. So that means to get a sum of 5, you could possibly get a sum of 5 4 times. So our 4 is our numerator. It's the number of times we think a sum of 5 should happen. 36 is our total number of sums we could get. So 4 out of 36 is our theoretical probability. You need to reduce that to 1 over 9. Everybody okay there? All right, last one. Let's talk about this theoretical probability. I gotta zoom out because I wrote a lot here. So this one is getting a sum that's an odd number. So first of all, remember, the sums can only go from 2 to 12 because 1 plus 1 would be the smallest amount and 6 plus 6 would be the largest amount. So of that, an odd sum would be a 3, a 5, a 7, a 9, or 11. In each of those sums, you have to think about how could you make a 3? How could you make a 5? How could you make a 7? How could you make a 9? And how could you make an 11? Remember, you can't have any numbers bigger than 6 and any numbers less than 1. So 0 plus that number doesn't count. So if you go through, I listed all of the different options. And remember, you have to switch both of the digits because a 1 and then a 2 is not the same thing as a 2 and then a 1. So I wrote all of those things out and I counted up how many different odd numbered sum options there were. So there were 18 different ones of those. That means the theoretical probability of getting an odd sum is 18 out of the 36 total. If you think about that, that makes sense because how many odd numbers are there versus how many even numbers? Well, there's half of the sums are even and half of the sums are odd. So it makes sense that our theoretical probability should be 1/2 when you reduce it. All right, feel free to go back and play through some of those examples again if you need to. Go back and write down things that you need as you're there. Don't forget to pause the video so you can write down things. And then when you're finished, I want you to work on this Desmos activity. Remember to click on the link, check your browser because sometimes it opens in the background, click join, continue without signing in, and then use your actual name if you want to receive credit for today's activity. If you have any questions, don't forget to talk to me during office hours. And like I said in the agenda, a video chat may be coming later this week. We will do more practice next class.